On a voltage detector circuit. And I'm going to show how I designed this from scratch here with a few equations and things, and I'll go through how I get to all the values and things like that. Then for the voltage level detecting circuit, let's start with this. Okay, what we're going to have is we're going to have an output resistance here. First of all, we'll put our supply voltage, we'll call that VCC. That'll be our supply voltage, positive supply. Then we have our output resistance. This resistor will be in series with the load. We'll call that one RC1. And then we have a transistor, NPN transistor. And then we have a emitter resistor to ground. We have a base resistor to ground. And then we have two resistors making up the supply voltage resistance. We have one going across here like this, and then another one going back up to the positive supply of the voltage supply. And I'll explain that later on when we get to that point. Okay, we're going to call this one here RC1. We'll call this RE. This one here will be called RB2. The transistor is Q2. This will be called RB1, and we'll call this RC1. This here has to be RC2, not 1. RC2. RC2, Q2, RE, RB2, RB1, RC1. Alright, let's do some calculations here and see what we can come up with here on the values for the resistors now. Okay, I'm going to choose for VCC, I'm going to choose 8 volts because I want this to run off of a 9-volt battery. So 8 volts would be a good voltage to use for that. I'm going to choose for an RC2 value here. I'm just going to choose a value of 1K ohms for RC2. And I'm going to choose a threshold voltage. This will be the voltage that it's going to detect, and then it's going to trigger in a high output. I'm going to choose 4 volts. That'd be half the supply voltage. I'm going to go with, no, let's go with 3 volts. I'm going to go with 3 volts. So voltage threshold VT equals 3 volts. Okay. Okay, now the threshold voltage is 3 volts. The threshold voltage is also considered the voltage at the base of Q2. We use that assumption. So at the base of Q2 here we have 3 volts. We have 8 volts for the supply. We have 3 volts at the base here. And we have 1K ohm for RC2. Okay, so now we want to solve for the value of RE. And we have to do a little bit of voltage divider equations here. If we assume that Q2 is saturated in this condition here, under saturation that'd be about 0.2 volts in that area there, so we can disregard that and just take that out of the equation completely. So if we want to solve for the value of RE, we have our supply voltage known and we have RC2 known, which is a resistor in series with RE. So if we use a voltage divider equation, we have VCC times RE, VCC times RE, all that divided by RE plus RC2. RE plus RC2. And that will equal the voltage at the emitter. That would be this voltage right here. Now we want to solve for RE. We can also assume for VE. VE is the emitter voltage. If we look at this, we see that we have a 0.7 volt drop between base and emitter. So if the base is 3 volts and we drop 0.7 volts from there, we have our 2.3 volts at the emitter here. So 2.3 volts is our emitter voltage. So we can put emitter voltage equals voltage threshold minus voltage base emitter, using that equation there. And that's what we did. We took the voltage threshold, which is also the base voltage of Q2, 3 volts, subtracted 0.7 to get 2.3 volts. Now, we have the supply voltage known, we have RC2 known, and we have VE known. So we have all the values here are known that we need, so we only have to solve for RE now. So by rearranging this equation, we can solve for RE. Therefore, by rearranging the equation, we end up with RE equals voltage at the emitter times RC2, all that divided by supply voltage VCC minus VE. We get that equation by using the voltage divider equation up here, and then just rearranging that to solve for RE. Okay, so VE or RE will be VE, which is 2.3 volts, 2.3 times 1 k ohm, which is RC2, divided by 8 volts, which is VCC, minus our 2.3 volts, which is VE, and that will give us our emitter resistor of value of 403 ohms. So then the closest nominal value would be either 420, or we can go with 390. I will go with 390 because that's much closer. So we'll use 390 ohms now for RE. So now we have RC2 chosen. We have VE solved by using the voltage at the base of Q2 as the threshold voltage. Then we also now have RE. So now the next equation would be RB2 equals 10 times RE, which would be 3.9 K for R2. So now we have RB2 is 3.9 K because we take 10 times RE. We use that equation there. Okay, so now that we have RB2 established at 3.9 K ohms, that leaves us with two resistors left over here, RC1 and RB1. In order to solve for those resistance values, we have to find the base current flowing through here. And the base current would be using Ohm's law. Voltage to base here we call VT. That's voltage to base. That's our threshold voltage, VT. So therefore IB2 equals VT, our threshold voltage, divided by RB2. So if we take 3 volts, divide that by our 3.9 K, we end up with 769 microamps. Now that we have IB2 established here, we can now solve for RC1 next, and by doing that, we can use another formula. I found that RC1 equals 0.1 volts dropped across it divided by IB2. If we assume 100 millivolts dropped across this value, the resistor right here, that gives a good value for RC1 for this kind of application. Okay, 100 millivolts divided by 769 microamps gives us 130 ohms for RC1. So RC1 is now 130 ohms. That leaves us with one resistor left over to solve for now. That value is RB1. To solve for RB1, we use one more equation, and that is this. RB1 will equal, if we take the supply voltage, VCC, we subtract the 100 millivolts dropped across here, minus 0.1 volts, and then we subtract the base voltage across here, minus voltage T, because remember that's voltage T here, so we're subtracting supply voltage minus the 0.1 volts across here and subtracting VT, which is the threshold voltage sitting here at the base, the ground. Now we subtract those voltages there, and that will give us the remaining voltage across RB1. So this is voltage across RB1, VCC minus 0.1 volts minus VT. Let's solve for that. Okay, so that's 8 volts minus 0.1 volts minus 3 volts gives us 4.9 volts dropped across RB1. So again, we can use our equation now for Ohm's law equation and take voltage RB1 divided by IB2, which equals 4.9 volts, divided by 769 microamps, and that gives us RB1. There's a value about 6.3K, so we'll use 6.2K for a nominal resistor. So 6.2K now will be for RB1. So now we have all of our values established here. We are assuming our transistor is saturated, so we have our RC2 value chosen as 1K ohms for output resistance. We solved for RE 390 ohms. Then we used our equation of 10 times RE to give us our 3.9K for RB2. And then we solved for the base current, or the divider current flowing through RB2 by taking the threshold voltage, which is the base voltage of Q2, and dividing that by RB2, and that gave us our IB2 current flowing through there, 769 microamps. Then we used another formula and said 100 millivolts dropped across RC1. So if we take that 100 millivolts divided by the current flowing through here of 769 microamps, gave us an RC1 value of 130 ohms. And then that left us with the RB1 value of 6.2K as we subtracted all the voltages, and then we divided by the we subtracted the voltages from the supply voltage, which is a 0.1 and the 3 volts here, and that gives us 4.9 volts dropped across here, and then we divide that by our IB2 value, and that gave us our 6.2K ohm resistor. So now we'll go ahead and do the next part of the circuit now to make this into a Schmitt trigger circuit now. Okay, so now this is the first part of the circuit, of the Schmitt trigger circuit, of doing the calculations for the resistor values. Okay, you can see it's nothing more than a common emitter amplifier. However, it is in saturation, so it's really a switch. It's operating as a switch right now because we're in saturation. That's how we calculate the values for. Now, since we're in saturation, that means then that we have a voltage drop across here, and there's going to be an idle voltage sitting across here. So let's find out what that voltage will be at the collector of Q2 under saturation of 0.2 volts across it. And now, this voltage is going to be sitting at the collector here. Under conditions of the transistor being saturated, we have 2.3 volts at the emitter. We add that 0.2 volts saturation voltage. Now it gives us 2.5 volts at the collector. What that means is that we have 2.5 volts, what's called standing voltage, which means is that when there is no input to this circuit, we're going to have 2.5 volts above ground on the output as a idle voltage, standing voltage without any input. Now let's redraw this because we're going to put one more transistor in here so that we can make this work as a Schmitt trigger circuit. Right now it's just a saturated switch. Alright, we're going to change this now into a Schmitt trigger circuit after we build this. We're going to build this and check and see how close we get to this voltage here first. Put our NPN transistor in here, and we'll put our 390 ohm resistor in for the emitter. It'll be 1K ohms. We'll put that in here at the collector. Resistor of 3.9K ohms, 2K ohms to one resistor, to positive, and 30 ohm resistor to the positive side of the battery from RB1, which are 6.2K. So now we have all of our resistor values established in there, and let's take some measurements now. Supply voltage is at 8 volts. Now we're going to check our voltage at the emitter. We want about 2.3 volts there. Here's our emitter right here. And we're getting about 2.2 volts. Okay, we're 100 millivolts off. We're pretty close. And let's check our base voltage. Now our base voltage is our threshold voltage, around 3 volts. So we're probably around 2 point something here. 2.92. So we're very close to our 3 volts. So we're within reason. The reason why, of course, is because we have tolerances of the resistors and transistors and things. So we do have tolerances to work with, and that's very understandable when it comes to electronic design, as long as we're within our range of voltage that we're looking for. Now let's see what we have at the collector here. If we have at the emitter here, which is 2.2 volts, we should have close to 2.4 or so at the collector if we're in saturation. 2.38. Okay, there's the voltage across the transistor from collector to emitter. 150 millivolts. So we are in saturation for the transistor. The transistor is acting as a switch. Okay, so back to our collector voltage here again from ground. We have 2.38 volts. That's very important to remember because we have a voltage at the collector here, even though our transistor is in saturation. But because we have this resistor value here, it has a voltage drop across here, we're going to have a standing voltage here. And that's very important for our next part of our circuit that we're going to be adding into that later on. Now, we have this transistor acting as a switch. Everything's working according to our design values here. How do we turn this now into a Schmitt trigger circuit, a voltage level detecting circuit? That's coming up next. Okay, this schematic's getting a little bit cluttered up here, so I'm going to draw it back down here again. I'm going to draw it more clearly because I'm going to show now how we're going to make this into a voltage level detecting circuit. Down here in the schematic, down here a little bit more cleaned up here. Again, this is Q2. This is RC1, RC2. This is RC2. This is RE. This is our RB2. This is our RB1. And this is our RC1. Alright, that's what we have so far. So we have at the output here, we have around 2.3 volts or so. Now, we have 3 volts sitting here at the base according to what we want to design that for. So here's how we turn this now into a switch. It's very simple. We take another PNP or another NPN transistor like this, collector here, emitter, and base. The base input, we can put a series dropping resistor here and let it go at that, and that's going to be our base input. That's it right there. We take our emitter and we connect it directly to the emitter of the first transistor. We call this Q1 here now, input. Now we have a voltage controlled switch right now. What's going to happen is when our base voltage here, when the voltage at the base of this transistor reaches a higher voltage than the base voltage here, this is going to start conducting. And when it starts conducting, it's going to start drawing current away from here, and it's going to cause the voltage drop across here to become less until this goes out of saturation and completely goes into cutoff. It's going to switch very quickly. It's going to have what's called regenerative feedback. It's going to take current away from here and put current here, causing this here voltage drop here to increase, causing this to decrease across here. Now we're going to build this and see how that works. All we got to do now is just add one transistor here like this, and we're going to see how that works now on the real circuit now. Add this here transistor right here, right in the circuit here now. Here's the series resistance to the base. The emitter connected directly to the other emitter of the other transistor, and the collector to the junction of the two resistors right here, RC1 and RB1. Okay, now let's put an input voltage into here and see what our output voltage becomes. Here's the circuit I have built now over here, and I'm going to put the input through a potentiometer here, and I'll show you how that looks here. I have a variable resistor where the tap in the center here. I have the one side going down to ground and the top side going to the positive side of the battery, and we just tap off the center of the potentiometer to the base. I have a voltmeter at the base right here. I have a voltmeter to ground, and I have a voltmeter at the output here. What I have here is the input voltage, and there's the output voltage. Okay. Now we have this set so that when we get around 3 volts at the base, we're going to have around 8 volts at the output. Okay, supply voltage. So right now we have a standing voltage, again as we said before, around 2.39 volts. Okay, that's the voltage under idle conditions when there's no input to the base. All right. Now I'm going to go ahead and turn the potentiometer here, and we're going to watch the base voltage and then watch the collector voltage as well. The base voltage is 1 volt. The collector voltage at the output is still at 2.39 volts. We're at 1.5 volts. We're now at 2 volts, and we're staying steady. We're at about almost 2.5 volts here on the input, and we're still staying steady on the output. As we continue to increase the input voltage, we are now at 2.8 volts, 2.9 volts, 3 volts. At 3 volts, we go to 8 volts on the output. As we come back down now, let's see what the hysteresis is on this. As we drop back down now, we drop from 3 volts down. Look how close. That's a very, from 3 volts, and it drops to 2.9, 2.8, coming up, 2.8. Well, I'm already there. So from 3, so look at that. Look how quick that goes. All right. So what that means is there's a thing called hysteresis. I'll see what that's about now. Hysteresis has to be sometimes, a lot of times, is designed into a circuit like this, which I did not do. Okay. Using the equations that I used here, I only used a threshold voltage for a input voltage, and that was it for the change. Hysteresis means is that you also solve for a lower cut-off voltage as well, upper voltage and a lower voltage, and that's the way it's done in a commercial circuit. In a professional way of doing this here, you would solve for the resistor values in that kind of a way using voltages. That's called hysteresis, and that is to give yourself a little bit of a see, mine's changing very quickly from high to low, okay, at 3 volts. Hysteresis means that you can design that to drop maybe at maybe 2.5 volts to give yourself some headroom there to take care of any kind of noise and things like that. Now, like I said, this is my version of designing this here from just experimenting, and that's why I came up with these here few equations here and things. And I'm only using just the 1 threshold voltage only, and that's why we have such a sharp change from the input to the output when it goes from high to low and low to high. There's such a sharp change there because there's no hysteresis that's built into it, designed into it, because I'm just doing it a very quick way of doing this here. But it's working for my purpose of showing how I'm designing a voltage threshold detector so that I can continue this on to build my pulse width modulation unit. Put this through a dynamic test. Let's look on the oscilloscope and let's put a sine wave in here, and let's convert this from a sine wave to a square wave, and let's do a little bit of a pulse width modulation right here, right with just a Schmitt trigger circuit, just using it as a threshold voltage circuit. Okay, we're going to do it on the oscilloscope now. We're going to set both the values here. We're going to set here's the input. We're going to set that at this line right here. And we're going to set this one, they're both together on the same line here. Now we're going to set both these two. They're on 5 volts on here. And we're going to set them both to DC, input and output on DC. As you see, the outputs are ready. If I put that, I'll go back to output. Now here's the output, and I switch the output down to DC. Already I'm rising. There's my 2.5 volts right there. I'm already 2.5 volts up. And you see why this is not going to work good for a load, because right now the load would be running, and we don't want that. We want it to be off until a valid input comes in. But we'll get to that later on, as I said. Okay, let's take a look at the waveform now. We're going to look at the input and the output waveform. And we're going to go ahead and turn the oscillator on here now. There's our input voltage right here, the bottom here. Remember now, this bottom line here is the 0 volt line, this here line that it's sitting on right now. We got them both on DC, so as I raise the potentiometer here, the output's going to raise up also. The whole thing's going to float up. Now, watch what happens when I begin to increase the voltage to the circuit now. The input voltage begins to rise. It gets to a certain value, and all of a sudden now we're getting our square wave output right here. We're getting that output as we're triggering out there now. Continue to increase the input waveform into the threshold voltage past the 3 volts, and now we keep on going further, and now we're full 8 volts. We're at full steady voltage now of 8 volts on our output. As we decrease the input voltage, now let's go ahead and make this look a little bit better. Let's make this a little bigger here. Okay, here we go. As it's rising up, there's our output, square waves, and now we're full. Come back down again, and so now let's remove the input completely so we can just take a look at the output only. And there's our square waves, and so there is pulse width modulation right there. That's pulse width modulation. The width of the pulse is being varied by the input voltage being adjusted by the potentiometer down here. Now I'm going to show you something else here about DC voltage across the load at the output. Take a look at this. Remember, we're at 2 volts now, standing voltage right here. All right, as we were explaining before. Now let's take a look at what we have here on the DC voltmeters. Okay, my standing voltage 2 volts. Now let's take a look at this here. Whenever that begins to come up, okay, now right now we're peaking at 8 volts, all right, but let's increase the waveforms about half and half, all right. Right now we're about half and half, so half of 8 would be around 4 volts, okay. So if we were to actually look at what we got pretty close here, at the DC voltage, we're around 4.8 volts, roughly around there. We're pretty close to half the supply voltage because of the width of the pulse being almost half and half. That's 50% duty cycle. So as we look at this now, if I keep that waveform right where it's at, I don't touch the potentiometer. If I turn first of all, let's put this back in here again. If I turn the oscillator off, this wave goes off, we're going to see that voltage go to a different value. All right. So I'm going to turn the oscillator off now. We lose the input voltage. Now we also lost the output voltage also. But now let me go ahead and adjust this now until we get our 8 volts. Okay, now we're at 8 volts again. Okay, so now we're back to 8 volts on the screen. All right, now watch this. At 8 volts DC right now, if I put the oscillator on now I got a square wave again. All right, now we're back to a square wave again. Look at the voltage now. We're back to around 5.5 volts. So what that is doing is this is taking the average of the supply voltage that's being applied to it. We're peaking at 8 volts, but because we're on half the time and off almost half the time, we're getting a value in between. This is maybe a little bit past 50% duty cycle. That's what they mean by duty cycle. Is if I remove the input waveform, there goes the input waveform, the output is way back up here at 8 volts again, and that's exactly what the DC shows. Put the waveform back in again, and now we start getting pulse width modulation. Pulse width modulation causes the actual DC value to go down. So now as I continue to change this here pulse width right here, here's the DC changing. Before, remember, we had from 2 to 8 volts. Now I can vary that in between. As the input voltage varies, I can vary the output voltage across the load linearly. See how that works that way? Because we're varying, and because we have now our pulse width modulation is working now. Again, if I remove the oscillator, we're now steady voltage. We're steady voltage here. Now if I drop the voltage again, we end up going from 2 to 8. 2. It's very slow. But again, put that back in there, and now we have a varying supply, or a varying voltage across the load. You see how it can actually increase it slowly and decrease it slowly, because we're no longer reading peak voltage. We're no longer reading peak voltage. We're now reading the average of voltage that this thing is picking up with respect to the amount of time it's on to the amount of time it's off per cycle. I'm not explaining it very well, I know that, but you get the point, is that if there's no input signal, you're going to either have a low voltage or a high voltage switch. With an input signal, now your voltage across the load is now varying according to the on-time to off-time ratio. That's what pulse width modulation is all about. Okay, I guess I gave a good demonstration there. Not a good explanation, but it does demonstrate there that it is working properly as a pulse width modulation unit at this point. However, I still need to add more circuitry, as I said, to bring that output voltage back down so I can drive a load from ground to positive supply voltage. And that's going to be coming up next now.